Well, welcome to Monday Night Calculus. My name is Curtis Brown, and tonight we are talking about limits and continuity. I am joined once again by Steve Kokoska and Tom Dick. Really excited to have these guys here. And we've got a few things going on tonight. I know that we always have the student problems posted down as a link down in the description. I've also got a link down there if you're interested in checking out Steve's book. He's got it there in the background of his camera, so you guys can check that out. Also, just wanted to make you aware that at the end of the session, I'll be putting my email address in the chat of the YouTube event, and you can email me. And I will give you a link to generate a professional development certificate. At the end of the session, I'll give you that information. And finally, at the end of the session tonight, or actually really tomorrow, I'll be adding a link to the teacher document that has all the solutions and everything. So if you're a student out there hoping to have all the answers already, sorry, you'll have to wait to the end of the session or tomorrow to get it. And if you're a teacher, just know that you can get that by logging back in and clicking on that description, expanding the description and finding the link down there. So Steve, I will turn it away. I think you're going to take it away from here.
Thank you very much, Curtis. Great to be with you and Tom again this evening. There was this rumor on the Facebook page, Curtis, that you had done your homework for this evening. So we'll have lots of questions for you
That's a
today.
great rumor.
Well, tonight we're going to talk about limits and continuity, and we've got some great limit questions, I think, here that'll all not only make use of some analytical techniques, but we'll see a lot of neat things with technology, graphically, numerically. Tom's got some great examples here, I think. So I'm going to start out by looking at a couple of, or at least one limit example. I'll turn it over to Tom and we'll go back and forth after that. I'm going to ask some questions. And Curtis, I hope you'll monitor the chat. I hope that participants will ask and answer some questions. So here we go.
I am on the chat.
Eventually we'll probably, Curtis, eventually we'll probably get to a problem or two that requires L'Hopital's rule, but not all limit problems do involve that concept, that idea. So let's first take a look at the limit as x goes to -3 of this rational expression. So one sort of natural thing that I think we might do is to take a look at the limit in the numerator and a limit in the denominator. And I see one quick thing already. That should be a -3 over there. So we're going to take a look at the limit as x goes to -3 in the numerator, the limit as x goes to -3 in the denominator. And if I plug -3 into both of those polynomial expressions, I do indeed get 0. So in fact, to evaluate those limit expressions, I can use direct substitution. So here's a question, first question, Curtis. I wonder why or what allows me to use direct substitution and what sort of property is going on in the background there? What allows me to just substitute in and to know that that limit is equal to that polynomial evaluated at -3? Okay, so in my way of doing things in my class, if I have this expression where I plug in, evaluate the limit in the numerator, evaluate the limit in the denominator, and I get a 0 in both, that's a signal, that's a sign to me that I need to do something. I don't know what that is yet. There are many different paths that I could follow, but it is a signal that I need to do something. I can't just decide on what the limit is right away. So in this particular problem, it seems sort of natural that what I'm going to try to do is to factor the numerator and to factor the denominator. And some good things happen here. I can actually cancel out this x plus 3 that appears in both the numerator and the denominator. And if you look kind of closely in blue, I've circled an equal sign here, and that's kind of important for me anyway. That equal sign says, well, that these two limits here are equal, but not the functions. The expressions are the same, are equivalent, but the functions are different. And they're different because their domains are different. And this is the way that I think about this. If I want to know what this expression is doing near x minus 3, I can ask, what is this expression doing near x equal -3? They're equivalent everywhere but at -3. And how do you, what is the limit all about? What's going on near -3? And how do I evaluate this limit? Well, that I can use direct substitution. And if I've done everything correctly, I get a -5. So a relatively straightforward limit problem to start out with. Let's not lose sight of some of these algebraic techniques, non-L'Hopital techniques here to evaluate a limit. Let me show you a little bit with the TI-Nspire. Tom and Curtis know that I really do enjoy using this machine. It is just amazing to me that this does computer algebra and quickly and efficiently. So what I did, probably overkill, but what I did is I first defined this function f on my TI-Nspire on the calculator screen. And there's actually a limit function built in. There's actually a limit template built in that even allows you to do one-sided limits, which is very cool. So I ask for the limit as x goes to -3 of f of x, and the calculator comes back and tells me the answer is -5. I'm feeling pretty good about this answer. On the right-hand side, I've got a calculator screenshot of a graph screen, a graph of this function of y equal f of x, near around x equal -3. Now, I took the liberty here of putting in a couple of tick marks. This is a -5 down here on the y-axis, and there's -3, and there's -4 along the x-axis. It's kind of interesting. I can trace along this curve if I want with the TI-Nspire. And I can also, as I trace, Tom reminded me, I can also type in a specific value of x. So I can trace along this curve and see what the value of f is doing near x equal -3. And I put a sort of a question over here. You know, it seems to me as I think about this, and I think about my pre-AP, or my AP pre-calculus, excuse me, you know, there ought to be a hole in this graph, but I don't see it there. And that's, I think, Tom and Curtis will have to correct me. That's because of the way that the TI-Nspire actually graphs, and we won't go into that, but it graphs just a little bit differently than, say, the TI-84, which is pixel by pixel. The TI-84 does a little bit more of, well, not AI, but a little bit more of analysis of the curve and filling in the gaps. Well, anyway, I feel pretty good about this limit. It sure looks like as x gets closer to -3, the value of the function is getting close to -5. To back this up even more, the TI-Nspire has a lists and spreadsheet page. I have a screenshot down at the bottom left-hand side. And I've got a couple of columns here. If you can see, this one is labeled x left and this one is labeled x right. Those are values as I get closer and closer to -3 from the left-hand side and from the right-hand side. And then in these two columns here, I am evaluating the function f coming in from the left-hand side from these values. So for example, f of -3.1 is -5.6667. And here is the evaluation of the function as I approach from the right-hand side. Well, if you take a look at these values here as I get closer and closer to -3 from both the left and the right, sure looks like I'm getting closer and closer to -5 numerically. I think I've probably beat this one into the ground. I feel pretty confident that the limit here is -5. We've looked at this analytically, remembered an important algebraic technique to solve a limit here. We've seen this done analytically by the Nspire. We can see it graphically. We can see it numerically. Tom, a little bit with the TI-84?
Sure, Steve.
Okay, here we go. There you are.
All right. Yeah. Let's see if I can find my TI-84 screen to share. And let's see. Pardon me for.
Have you got the emulator?
I've got it. Yeah, let's see. Okay, found it. All right. It was off my screen. So what I've got coming up, I hope, is it's actually the online version of the TI-84. So
very clear.
See that? Great. All right. And it came up in the y equals window. So I'm just going to go ahead and enter the function that Steve was looking at there in part A. And so let me go ahead and enter it out. I'll put the numerator in first here. So that's x squared. And it's actually a plus x minus 6. It's all in the numerator. Let me close that off. And now we'll divide by the numerator, put that in parentheses. So we've got x squared plus 7x plus 12. I think I got that entered in. Okay.
Good.
And going to graph this. I'm going to graph this. It's kind of my favorite window is the zoom decimal window. So that's the number 4. And for this particular limit, just looking at it graphically, it's not an ideal window because we are approaching -3. So I'm just pointing to that on the screen there. I hope you can see that. And the graph has kind of gone off the screen there, so we can't quite see. And I noted, thinking ahead, Steve's already kind of illustrated what we think the limit is he actually analyzed it. The limit is -5. I'm just going to change my window a little bit here. Let's see. I'm going to leave my x-min and x-max alone. Let me just make my y-min. Let me go down to 6.1 instead of -4.1. And let's try graphing that again. And boom, there we actually see this break. It's actually quite a, Steve mentioned wanting to see a hole in the graph. Because the graph is so steep, it looks like there's kind of a major graph, but that's just a single pixel over there. And we can kind of see that when we trace over to there. Let's see. Well, let me actually jump all the way to -3. So I'm just going to type in -3 for x, enter that. And I actually don't see anything at all, except at the bottom of the screen, I see something that's interesting. It says, okay, when x is -3, y is equal to nothing. It's undefined. And when I say nothing, I don't mean 0. There's just no value whatsoever. Now, if I trace now to the right, at -2.9, I see there's about -4.45. If I trace to the left a couple of pixels, -3.1, -5.667, you can see there's quite a gap in values there. We don't really have as much of a sense of what the limit value is from this graph. Now, what we could do is, since I'm between -5.5, -4.5 in the y values, it seems that what I could do is actually change my window and make it much more narrow vertically. Okay, so why don't we make my y-min -5.5, and my y-max, let's make it -4.5. So that's just my entire screen vertically will just be a single unit. Let's graph again. See anything? What's happened here? Okay. So the jump is actually so big. If I was to trace and go to -3, well, it's still empty. If I trace over one value, I'm still seeing the readout. But I'm not seeing any graph at all because
why?
It's continuity. Yeah.
It's off the screen, isn't it?
Yeah, completely.
Yeah, the steepness of the graph at that point, the rate of change between, I guess, -3.1 and -2.9 is so great that that jump is so large that it just,
Tom,
that width of a pixel
exactly
jump is larger than what you have in your y values.
Okay.
Tom, just for the heck of it, would you try something even closer to -3, like -3.001?
Sure. Yeah, we could enter in a value. We're not seeing any graph here because of this phenomenon. But if I actually typed in -3.01.
So that's actually off the screen too. That's interesting. Yeah. They're all.
No, that's right
No,
there.
that should be there. Yeah, so
Yeah,
what? That's
it's
right.
right in the middle.
Yeah.
It's not corresponding to a value that was plotted, though. See, our plot, the plotted values are going by 0.1 in
Okay.
that decimal.
I see. I
So
see.
this is it's putting the crosshairs where the point would be,
Yep.
but it didn't plot that thing there. So
Gotcha.
so let me try something.
Oh, that's weird. That's really weird.
Yeah, it's kind of interesting. So what I'd like to do is kind of show what we'd like to do is kind of be able to zoom in on this point horizontally. And there's kind of a neat way to do that on the TI-84. Let me show you all how you can do that. I'm going to go to the zoom key, but to the format. Let's see. And excuse me, I didn't really mean to do that. I actually do want to go to the zoom key, except go over to memory, zoom memory.
Mm-hmm.
And if you look at the bottom there, it says set factors. Okay. So what I'm going to do is I'm actually going to set the X factor to 10. That means when we zoom in, the X values will change by a factor of 10, either zooming in or zooming out, they'll be multiplied by 10, okay? I'm going to change the Y factor to 1, which means that the Y values won't change at all. So it's a way for me to be able to zoom in entirely horizontally. Okay, let's see how this might work. So I'm going to regraph. In fact, let me go back to a zoom decimal window so we get our
Original one.
Original graph there.
Yeah.
And let's see, I do remember that we did want the window to go down to like negative, let's go to negative 6.1. There we go. So we graph it, so we'll see that break.
Gotcha.
And what I'd like to do is actually zoom in horizontally down at this point here. So let me set my window up. Let's see, what we want to do is really be centered at -3, okay? So I could put in, say, -3 minus 5 and -3 plus 5. And if we graph in that window, we can see that we still have that gap, but now it's centered in my screen, horizontal. Okay.
Okay.
All right. Now I'm going to zoom in. And my Y values have not changed at all in this window, but you can see now the graph is, what's the real effect of that? Let's look at the trace here. Yeah, now notice I'm right at X equal -3, so it's still undefined. But now this looks more like just a little tiny hole in the graph. Yeah. If I trace to the right, you can see that the Y values are the X values are much closer to -3. The increment is much smaller. Okay. So at -3, I could zoom in again. And again, this will be just horizontally. And you can see the effect of this is the graph looks like it's flattening out. But my window, if I was to check my window, you can see the values are very, very close to -3 all the way across the window. So we're really having this chance to get closer and closer to -3. I think something you suggested, Steve, we could do is just type in some values in our trace that are very, very close to -3, like -3.001. Let's try that out. And I can see the Y value corresponding to that is -5.006006.
Uh-huh.
I typed in -2.999. It's
Mhm.
negative 4 point. And so I can see those Y values getting really, really close to -5. And I think that's actually a really kind of powerful way to be exploring limits, both numerically and graphically, is by graphing, so where you can see that hole, and then actually doing the trace feature while you're actually inputting numbers that are getting successively closer and closer to your target value. You can also do that in something akin to the list in spreadsheets. I think what I'll do is hold off a little bit on showing that.
Okay.
You want to make one point about this hole that one.
Whoops.
Uh-oh, did we lose Tom?
Did we lose him?
As Steve mentioned, you don't see it on TI-Nspire. We wouldn't see it on the TI-84 unless that actually lines up with one of the pixel values that's being plotted. Okay, so there's a number of ways you can do that. If it's an integer value that's your target, zoom decimal window is going to kind of naturally make those land right on your pixel values. But you always can do what I did when I went to my window and I added and subtracted the same amount from my target to set my X-min and X-max. So notice here, our target is -3. That's the number we want to approach. My X-min is -3 minus 0.05. My X-max is -3 plus 0.05. If you set your window in that way, you're guaranteed that your target's right in the middle of the screen. So it's kind of a good best practice when you're using the grapher to explore limits. I think I'll turn it back over to you, Steve, unless Curtis, you have anything you want us to look at?
No, I don't think so. I really appreciated you zooming in on the X coordinates there to really demonstrate. I think that's a powerful demonstration. Yes, we get this great visual on the TI-84 because of the pixel graphing, and that's really handy. But I think, zooming in to where the domain that you're looking at is extremely narrow, right around that value -3, and yet there's only one pixel that still isn't being plotted. And
Yeah.
I think that demonstration of, we have this infinitesimally small uh, uh, dot, if you will, that's the undefined point. Otherwise, that function, is defined everywhere on either side of that. I think that's just a cool way to demo that, that you zoomed in on that. And you could continue zooming in and seeing that almost approach a line right there, right? That local linearity thing, and really see that.
Yeah, in fact, one could actually characterize functions that have limits, and that would include continuous functions, because what makes a function continuous at a point is its limit. It has a limit at that point that matches the function value. Both those types of functions, if you zoom in horizontally on them, I'm going to zoom in one more time here. Let me move over to the -3, very close to it. Successively zooming in horizontally will make the graph appear horizontal, okay? Except for, of course, that one point.
Yeah, you've lost it because you.
Yeah, I've lost it with the, whoops, there we go. I better quit while I'm ahead here. Go back to the graph. Whoops, there's the graph. If I was to trace and type in -3, yeah, I wasn't right on -3. Oh, -3. Let's see. Oh, maybe it's because it's thinking it's undefined there. I'm not sure. Let's see. Let's go back to the graph, turn on the trace. Let's see. I should be able to type. Oh, I know what's happened. The -3 is not even on the screen. So I was off just a little bit. And by zooming in horizontally, I got it off the screen. So that's my bad. So -3, I think, is all the way to the right. It's actually off the screen. So I should quit while I'm ahead. Turn back over to Steve.
We'll catch you back up here, Tom.
Okay.
So, Tom, interesting question that you made me think about, and we've actually asked a question about this at the very end of this problem set. I don't know if we'll get to this or not, but I wonder if there is a way. We'll pose this as an open question. You have shown us how to graph a function and position or set the window so that we can see that hole in the graph. I wonder if there's a way to graph a function and see two holes, if it has two there, at, let's say, at rational numbers. So I wonder if there's kind of a standard way to do that, and we'll leave that as an open question and see if it comes up with that. Okay. All right, I'm going to take a look at B. Cheapers, we're going to be here until 10 o'clock, Curtis. I hope you've got time for this. B is another rational expression, and the very first thing I'm going to do, of course, is to check the numerator and the denominator, and indeed, in this case also, the limit in the numerator and the limit in the denominator are both 0. So again, that's a signal to me that I need to do something. So I'm going to try the same sort of thing here. Same sort of algebraic technique. I'm going to factor both the numerator and the denominator, and some good things happen here too. I've got an x plus 3 squared in the denominator. I've got an x plus 3 in the numerator, so I can cancel one of them. And I'm left with this expression, and I've got to be a little careful here. I'm going to say carefully or cautiously that I can now evaluate this limit. I can now get an answer, and my answer is that it does not exist. And I'm going to justify that in just a second. And I've got to be careful here because I cannot write infinity or minus infinity in this case. This is kind of a neat problem that we've come up with, I think. So I'm going to justify that DNE in just 1 second, but off to the side, I left a note for myself about calculus, AP calculus abbreviations. Tom and I have frequently asked this question, well, you know, what sort of abbreviations can students use on the exam? Do the readers understand things like DNE? And yeah, I believe they do. Can they use an abbreviation like MVT for mean value theorem or IVT for intermediate value theorem? Yeah, I think that's okay. But there's probably some line in the sand, and I'm not sure exactly what that is. I think after those 3 or 4 of them, I would suggest that your students write things out, even under the pressure of a timed exam. Try to write things out. So let's go back to this here for a second, and why I have to write DNE here and not infinity or minus infinity. And I think the reason for that is that this expression has different sort of behavior as x approaches -3 from the left and from the right. Let's see, is this x is approaching -3 from the left? Well, let me just take a look at the numerator here. This is going to what? -5, I think. What's the denominator doing? Well, let's see, as it approaches -3 from the left, -3 from the left. So that means it's approaching like -3.1, -3.001. So that means this is getting very, very small negative. That's the way that I usually abbreviate that in my class. I cannot use that abbreviation on an AP Calculus exam. But between me and my students, we understand that. That means that that expression is getting closer and closer to 0 through negative numbers. That means that fraction is getting larger and larger positive. So this expression is going to plus infinity. As x approaches -3 from the right-hand side, well, this is still going to -5 in the numerator, but in the denominator, this is going to 0 through small positive values, and that drives that whole fraction to very, very large negative values. So this expression, this limit, is equal to minus infinity. So I'm sorry, I'm going to use my hands here a little, Curtis. As we approach -3 from either side, the behavior of this expression is different. On the left, it's going to plus infinity. On the right, it's going to minus infinity. So I think I've got to write this here does not exist. Let me take a quick look at a calculator screen or two here. This is kind of neat. I didn't expect to see this, but this is kind of neat the way this happened on the TI-Nspire. I defined my function f of x, and I used a limit template to ask for the limit as x goes to -3, period, not from the left or the right. And yeah, the calculator came back and told me undefined. Now, I did not do this here, but I believe that if I looked at a one-sided limit, the Nspire would come back with either a plus or a minus infinity, the correct plus or minus infinity there. So that's kind of cool. it interprets this correctly. It understands that the behavior is different from the left and the right and tells me that that limit is undefined. That's kind of neat. And on the right-hand side, I've got a calculator, pardon me, a graph screenshot. And I took the liberty of putting in a dashed vertical line here to represent the asymptote. There's the -3 here on the x-axis. And indeed, as I approach -3 from the left, the function is going off to +infinity. From the right, it's going off to -infinity. The limit here of this expression, this function, does not exist. Pretty good. Tom, you want to do anything numerical? You want me to take a look at part C first?
Yeah, let me go ahead and do something numerically quickly, Steve.
Okay,
Get
deal.
back to you. Okay.
Okay, there we go.
Okay, let me get my screen up there.
Oh, that's an email.
Oh, that's weird. Okay, let me let me stop the share and try that again. All right.
Okay.
Thought I was on my 84. I evidently was not. All right.
Curtis, any questions or answers in the chat while Tom's doing that?
Here we go.
Oh, good.
That looks better.
Other than Mark Corrali saying that there's an abbreviation SATSS is not accepted. Steve and Tom said so. And there is a question as x approaches 1, then sine x divided by x is
Oh, we'll get there.
sounds like you guys may have an opportunity to explore that sinusoidal stuff.
Okay, cool.
In a minute. And outside of that,
Okay,
nothing
thank
else.
you.
All right.
So I think that's a plus. It's
9, right?
Well, it's -5x. Oh, pardon me. I beg your pardon, Tom. It's +6x + 9. Yes, that's correct.
Okay, so let me delete that. Yeah, I just edited my Y1 there.
Yep.
Okay, so that was the new function that we're looking at. Let me just graph it in a zoom decimal window, and we kind of saw. It's hard to tell. The graph actually looks quite a bit like the one we had before, but now they're at -3. You were showing that asymptotic behavior, vertical asymptote. I want to kind of look at this numerically in a different way, and it's kind of my preferred way when I'm using the 84. People might say, well, you're going to use a table feature. What I'm actually going to do is go to the stat plotter and go into the stat editor where I have my lists. I just wanted to show you some techniques that make it really easy to look numerically at limits. So in my L1 here, what I'm going to do is actually populate that by hand. I mean, you could use a sequence function or something like that, but I'm just going to put how close we want to get to that target value. So I'm going to start 0.1 is fairly close. Then 0.01, 0.001, 0.0001. And just for illustration, I'll just stop after about 5 of these. So you notice I'm just going in by a factor of 10 each time. Okay, this is how close I'm going to get to the target value. Okay. And then in L2, let's see, the target was -3. For L2, I want you to notice what I can do is just type in, okay, -3 plus L1. And I get a sequence of values that get closer and closer to -3 since I added, it's from the right-hand side, okay? Now, you might look at it and say, well, those last two are -3, but if we scroll down, notice that at the bottom, I'm getting a more accurate readout of what that number is. It got rounded off for display purposes, but it actually is -2.9999. And there's even closer, okay? So those are numbers that are getting close to -3 from the right-hand side. If I go up to L3, I could just put in -3 minus L1. These will be coming in from the left-hand side. And again, if I scroll down, we can see those last two values really aren't exactly 3. They're getting closer and closer to, excuse me, aren't exactly -3, but getting closer and closer. And now we can go to L4 and just bring up Y1. I'll go to my Y variables, get my Y1, and evaluate it at, let's see, if I want to do it from the right-hand side, I would put in L2. And I see those values. And if I want to come in from the left-hand side, I'll go to L5 and put in Y1 of L3.
Tom, I would just comment that that's an interesting syntax, that we wouldn't write, say, on a piece of paper. But the calculator allows us to do that, to evaluate a function with an argument that is a list. And the understanding is that it's going to evaluate the function at every member of
Everything in the list
every
and give you
element
that list of results. Yeah.
Yeah. Interesting syntax. Yeah.
And so here numerically, we can see, well, as I come in from, let's see, L4 is giving me these values.
Yep, coming in
and I
from the
plug
right.
in the values. So coming in from the right-hand side, oh, wow, these are large magnitude numbers that are negative. Okay, so it's really getting large magnitude negative, while coming in from the left-hand side, it's getting very large magnitude positive numbers that are just getting bigger and bigger. So this is giving me that sense of what I saw in the graph of approaching from the left-hand side, it's getting larger and larger, approaching from the right-hand side, getting more and more negative. And so the limit doesn't exist. The behavior is so different from either side.
Hey, Tom.
Yes, sir.
And you can stop me if I'm stealing a little bit of your thunder, but are you planning to look at the table and make use of the table for an exploration similar to that?
Well, you can go ahead and instruct me, Curtis, if you'd like. So
okay. Okay. So
Uh-huh.
let's do something real fast. Let's go to the table settings. Go second
Table
in
set.
the window.
Okay.
Yeah.
This is the table set.
And let's go ahead and change the independent variable to ask instead of auto.
Okay.
And now if you go to the table, so second in the graph key, you'll be in a table that kind of gives you the ability to input values for X, and they'll be subsequently evaluated for Y. So now you can do that evaluation as you approach -3 from, let's say, the left-hand side. So like -3.1 and then -3.01. And see that it's a little less formulaic in utilizing the utilizing the sequence or whatever. But the table with independent on ask is a pretty powerful tool for doing that exploration via the table here. And kind of a quick interactive tool. And if you pop in -3, you're gonna get that error evaluation right there. So
Yeah.
you'll see
No,
that.
it's really quite nice. Yeah.
Mhm.
What this does do is you would have to type each one of those, and
Yeah,
I'm
you
not
have to do
opposed
them
to
one by
that at
one.
all. Type them in individually, and I
You
think
have to do them
starting
one by
off, that's a
one.
really good thing to do.
It
Uh,
forces me to slow down and kind of concentrate on I'm getting closer to my discontinuity.
right. Where I find that stat strategy is especially nice is if your target value is a number like pi or something
Yes.
like that, where, you know, with your one list is how close you're going to get to it, and all you have to do is put people like pi plus that, pi minus that. It generates then, you know, nice input lists for this. But
yeah.
If anything, yeah, no, I think this is a beautiful way to do it. And so you can see,
For these nice integer values,
so
the ask mode does help me.
So we can get really, really close. Ask it.
You can get awfully close.
That in. Oh, that
Oh, how about that?
That was too close.
That error is different. That's errors because it overflowed, I think, in terms of.
You got too close there.
Yes. So let's try another one.
I think if you, I wonder,
let's try that.
What happens if you give?
That's so, Tom, stay right in that column if you would. Just arrow up one row to the -3. Yes. So, Curtis and Tom, help me with this. So, in this table feature, which I really do like, I think this is really cool. In the table, as we look at it, we see numbers displayed usually with maybe 4 numerical places.
Yeah.
But if we highlight it, we see more down at the bottom. Is there any way to increase the size of those columns, Curtis, to see more digits? No? Okay, they're fixed.
No, they are fixed columns.
Okay.
Yeah, that is something you can change on the Nspire.
Right.
List and spreadsheet feature, you can actually make your columns wider to accommodate larger expression. Yeah.
Okay.
Though, be quick to point out on the 84, even though those column widths are fixed, it is reading out there at the bottom what's actually in there to a much higher. But this was actually something that was a little bit surprising to me, that we actually got an error. This really was too close for the calculator to numerically come up with a value for that.
So what do you think is happening? It's overflow?
I think you blew out the top.
I think it just got too, it was larger than it was able to express.
Really?
I guess, that's my guess. I'd have to.
Okay. Either that or it was too close to -3.
Yeah, and correspondingly get much closer on the, let's see, this would be the right-hand side of -3. Yeah, I see that. Yeah. Again, though, it's illustrating, wow, really different behavior, whether if you're very close to -3 on which side of -3 you're on, how different the results are. Okay.
Pretty cool.
Oh, I'll stop the share there. Back to you, Steve.
Okay. Thank you, Tom. All right. There we go. Well, we've got another one, which finally I think is a little bit easier to do. It's again the limit of a rational expression, the quotient of 2 polynomials. And here again, I checked the numerator, and I found that as x goes to -3, the limit of the numerator is 0. And this time when I checked the denominator, I got a 30. That's kind of cool. This is not 0 over 0. And so that says to me, you know what? I might be able to evaluate this limit right away. And in fact, since the numerator is going to 0 and the denominator is going to a non-zero value, 30, this limit is actually just plain old 0. Very easy to evaluate. Just to double check everything, on a calculator screen over here on the left-hand side, oops, I'm sorry about that. On a calculator screen on the left-hand side, once again, I defined my function and used the limit template and got a 0. And on the right-hand side, there's a graph screen illustration. There should be no hole there or anything. The graph of this function f does, in fact, cross the x-axis at the point -3. So I feel very good about this one. I'm still in that mode, Tom, of explore and get an answer and then confirm, as we used to learn with technology in the very beginning. Let's explore this, see what the answer might be, then let's work it out analytically, and then let's confirm. So I feel pretty good about that one. Let's take a look at a couple of others. Is that all right, Tom, before you do?
Sure, absolutely.
Let's take a look at a couple of others here, maybe a couple of others analytically, and then Tom maybe has some more technology here. This is the limit as x goes to 0 of the sine of x divided by x We're going to get a little bit of more calculus in this one. One of the very first things I did here is I took a look at the limit of the numerator and the limit of the denominator, and again, it's 0/0. And that's something that tells me that I need to do something. Your AP calculus teachers will remember that this limit expression occurs when we first start to take a look at the derivative of trigonometric functions. I don't know if you are there yet in the curriculum or in your schedule, but that's where this first appears generally. And how do you get that limit? Well, the standard way to do this is by a geometric argument, and I'm not going to go through all of that. But the standard way is a geometric argument that involves a figure that might look like this, and that leads to an inequality like that. And you can kind of feel the squeeze theorem coming into play here because we know a little bit about the cosine function. We know this function 1 is constant. And we're able to squeeze that sine of theta over theta and get a limit. Now, just to sort of support all of this, on the right-hand side, I have a graph of the sine of x divided by x, and I added that hold there. This function is not defined at x equals 0. I can't divide by 0. But I feel pretty good about this limit being 1 because of the nature of this graph. I'm feeling pretty good about that. Here's another way. I'm sorry, go
Hey,
ahead.
Steve, before you go too much further on this,
Yes.
related to the previous problem,
Yes.
the someone in the Facebook group asked if an infinite discontinuity, where the values are growing without bound on the positive direction, could be described as the limit diverges instead of the limit does not exist or infinity. What are your guys' thoughts on that language? The limit diverges.
I'll give you one idea, and Tom will have a better one, I'm sure. I don't think I've seen that terminology used in AP Calculus, Curtis.
Okay.
I sort of understand it. I understand the language. The limit diverges. To me, that means it does not exist. In general, I would say in my class, if I know that the limit does not exist, but I can describe the behavior, for example, as going to plus or minus infinity, I would like to see that additional information in my class. So the bottom line on the exam, I don't think you'd see that phrase diverges in that case. I think it would be either does not exist or it would be plus or minus infinity. Tom?
Yeah, I think that language, I think it's stemming. We do use that language, but I think it's restricted to the behavior of an infinite series. And
Yeah.
so an infinite series,
Sure.
when the limit of the partial sums approaches infinity, we'll say that the series diverges. And so that's that kind of associating that term diverges with a limit going to infinity, I think is probably stemming from its use in the series context.
Mhm.
But yeah, it's a little bit awkward in the function context, I think.
Yeah. I don't know if I would.
I can see where it comes from, but I think describing the limit as approaching positive infinity or approaching negative infinity, realizing that when we write the limit equals infinity, we're not saying that the limit exists. It's actually just describing why the limit does not exist in a more quantitative way, I should say, in terms of the behavior.
Okay.
Good
Well, that's good. I was just curious and saw an opportunity to step in there.
Okay, so down at the very bottom here, of course, this limit is very easy to find if we use L'Hopital's rule. The limit in the numerator is 0, the limit in the denominator is 0, so we can take the derivative of the numerator, derivative of the denominator. Derivative of the sine is the cosine, derivative of x is 1. Cosine is a continuous function. I can use direct substitution here, and so that's 1 over 1 or just plain old 1. So I see a nice graph here. I can use L'Hopital to support this, but just a reminder that sort of the traditional way to do this is with a geometric argument, because at this point in the class, you probably have not talked about L'Hopital's rule yet.
Say, Steve,
Yes.
if I could, with that limit you just did,
Yes.
put in a plug for the power, especially early on, of employing some numerical and graphical explorations of limits.
Yes.
This kind of classic geometric thing that you've shown, I think that's still good to show, but I have found when for this limit in particular, students found the numerical and graphical evidence to be really more compelling than
Yeah.
that. The geometric
The
one
geometric
is
one.
quite complicated.
Oh, yeah, it is. There's no question.
Students
Yeah.
will often lose the forest for the trees.
Yeah.
But look at the graphical and numerical evidence, and it's just like, yeah, the limit's got to be one. It's just so compelling. So
Yeah. Yep.
I'm not saying those replace a proof of the limit, but
Mhm.
I'm saying that they do provide very powerful evidence for students.
Agreed. All right, here's another one. This limit, I think, also appears perhaps first when you take a look at the derivative of the sine function by definition. This is the limit as x goes to 0 of cosine x minus 1 over x, and I'm going to look at the numerator and denominator as usual. The limit in the numerator is 0, the limit in the denominator is 0. Pretty straightforward calculations there. And this is another sort of, not trick, but another technique that we often use in evaluating limits. What I'm going to do here is to multiply, the way that I talk about this anyway, is to multiply by 1 in a convenient form. So I'm going to multiply by 1 in that form, cosine x plus 1 divided by cosine x plus 1. How the devil did they come up with this? Well, I don't know. One way to think about this is that if I use that in the numerator, I see the difference of two squares. That seems like a good thing. So I'm going to multiply this out here, and I'm going to get this in the numerator, cosine squared minus 1. I've got x times cosine x plus 1 in the denominator. Right here, I'm going to use a trigonometric identity. I think that's correct. In the next line, I'm going to bring that minus sign through the limit symbol. Remember, constants pass freely through limits. And the next thing I'm going to do is actually split up the remaining terms over here into two sort of fractions. And then what I'm going to do is apply a limit law. The limit of a product is the product of the limits if the two limits exist. Well, I know that one of them does. I'm not sure about the other one yet, but I'm going to justify that in a minute. So I'm going to use some limit laws to get to this section and to this line, excuse me. We just found this limit a minute ago. That one's 1. And let's see. Sine x is continuous. The denominator is continuous. Direct substitution. Jeepers, after all of that, this expression is going to 0 minus 1 times 0. Jeepers, after all of that, that limit is just plain old 0. Now, I didn't add in a list and spreadsheets page here or a graph screen, but as Thomas suggested, another good way to look at this is with a list and spreadsheets, the table of values, or actually the graph of this function. That's a nice one too. I think I've got some more here. Let's see. Hey, here's one. A quick one. The limit as x goes to 0 of the inverse tangent of x divided by x. Well, again, I'm going to start off by taking a look at the limit in the numerator and the limit in the denominator. Both of those are going to 0. Wait a minute, how do I know about the numerator? Well, I know a little bit about the arctangent function and what that looks like. I know that it is continuous. Jeepers, what's the domain of that function? We might think about that for a second. But it is continuous at 0, so I can just plug in 0. That limit is 0. And in this particular problem, I don't have a sneaky algebraic technique. I'm just going to use L'Hopital's rule here. I'm going to take the derivative of the numerator. 1 divided by 1 plus x squared. I think Tom and I are often asked this question. Should my students going into the exam know the derivative of the arctan function? And yeah, I think so. I think they should know that one. A little bit of simplification. 1 divided by 1 plus x squared. Direct substitution. That limit turns out to be just a plain old 1. Nice problem. Kind of a neat problem. We'll just pose this question for the participants. Curtis, I wonder what this limit says. If I can explain this in context here, what does this limit say about the graph of the arctangent and the graph of x, y equal x, near 0? I wonder if we could explain that. We'll leave that as sort of an open question. Here's another one. This kind of a problem frequently occurs, I believe, on the multiple choice portion of the exam. I'm doing this sort of in general with constants A and B, but generally on the exam, they would have specific constants. I'm going to take a look again at the limit in the numerator, limit in the denominator is 0, and here I'm going to use another sort of algebraic technique. I know, I just did this one, I know the limit as x goes to 0 of the sine of x divided by x. And in fact, I can think of those arguments as being the same, the sine of stuff divided by stuff, as that stuff is going to 0. I'm going to keep that in the back of my mind. So what I'm going to do here again is to multiply by 1 in the convenient form, because my goal is to try to make this argument and the denominator look the same and go to 0 simultaneously. So let's see if I've done this correctly here. I'm going to multiply the denominator by 1a over a, and I'm going to group some things here. I'm going to bring one of these a's over here. I'm going to bring the b over there, divide by fractions. There's my a over b. That passes freely through the limit symbol, and now I'm going to make a substitution. You know, substitution is not just for integration. I'm going to let t be equal to ax, and I've left out just a little bit here. Maybe I should put in a little bit more. As x goes to 0, t goes to 0 also here. So this is equivalent to me asking the limit as t goes to 0 of the sine of t divided by t. And son of a gun, I know that answer is 1. And so this answer is a over b. Now, I'm pretty sure that your students are excellent at this. They have sort of memorized this process for arbitrary constants a and b. And this sort of a problem, I think, occurs often on the AP exam, not only in the multiple choice portion, but sometimes is a part of the free response question. Very good. Let me take a look at another one kind of quickly, and then I'm going to skip ahead here. This is a limit as x goes to infinity of a rational expression. And just to remind you of another algebraic technique in this kind of a problem, since the numerator and the denominator are both increasing without bound, what we generally do is multiply by 1 again in a convenient form, 1 divided by x raised to the highest power in the denominator. So let's see, 1 divided by x squared, 1 divided by x squared. I'm going to multiply all the way through. I'm left with this expression, which looks kind of awful, but easy to evaluate. As x goes to infinity, these expressions are going to 0, and I'm left with 2 divided by 3. And yes, you're absolutely right. That's the ratio of those leading coefficients. Now, we've got a couple of other problems here similar to that one where the powers on x change a little. I won't go through all of those. I'd like to end by taking a look at this one limit problem, if I can here. This is one of Tom's and mine favorite problem here to investigate graphically, to investigate numerically. This is the limit as x goes to 0 of 1 plus x raised to the 1 over x power. Now, this is in an indeterminate form. It is in an indeterminate form that is not covered on the AP Calculus exam. Students would not be tested on an indeterminate form of this kind. But you know what? This is a neat problem. This is math that's good for the soul, and I think would be neat to look at tomorrow morning at 8 o'clock. What happens here as x goes to 0? Well, one thing that I thought about is, well, as x goes to 0, the sort of base here is going to 1. That's pretty straightforward. But I couldn't tell exactly what was happening to that exponent because I'd have to look as x goes to 0 from both the right and the left. As x goes to 0 from the right, this is getting smaller and smaller, positively driving the fraction to infinity. As it's going to 0 from the left, the denominator is getting closer and closer to 0 negatively, driving the whole fraction to minus infinity. So this is going to 1 raised to the infinity or 1 raised to the minus infinity. And I don't know what that is. That's an indeterminate form in either case. I'm going to take a look at one of these as x goes to 0 from the right-hand side. The way to attack this sort of a problem is to let y be equal to the original expression and take a look at the log of that expression and do a little bit of simplifying. Make use of some properties of logs. The log of 1 plus x, that argument raised to the 1 over x power, I can bring that out in front. I'm left with this expression as x goes to 0 from the right. This is now going to the log of 1, which is 0. This is going to 0. I can use L'Hopital's rule. Derivative of that log function is 1 divided by 1 plus x, a little bit of simplification, and I'm left with 1. This is kind of cool. Now, I'm not done. That's the limit of the log of the expression. Now, there are several different ways to write this. Here's the way that I like to do this. I'm going to go back to my original expression. That is the limit as x goes to 0 of y. I'm going to rewrite that using sort of a cancellation equation. That's the limit as x goes to infinity of e to the log y. What's log y going to? Well, we just showed that's going to 1. That means this limit is e. And in fact, this is one of the definitions of e, and that's really cool. Now, we have to end on that, but I'm going to leave you with at least 3 problems to look at and to consider. Here are at least 3 other limits to look at. And there's a crazy graph that I have produced over here for this expression, for this function, 1 plus x raised to the 1 over x power. It's even weirder, I think, if you do this on the TI-Nspire. You should try that tomorrow morning and see if your students can explain to you what's going on. And Curtis will try to post these answers tomorrow. Terrific.
Well, thanks, Steve. I really appreciate you tackling all of that, and Tom for all the tech stuff. That's great. I'm going to put my email in the chat for those folks who are looking to get that professional development certificate. Curtis@ti.com. You can certainly reach out and get that professional development certificate. Otherwise, we'll be right back here, same time, same place, in about 2 weeks.
2 weeks, yep.
So we will see you guys on September the 22nd. Is that right?
Very good. Yep.
I think that adds up correctly. 14 days from now. So have a marvelous 2 weeks, and be looking for those solutions here sometime tomorrow.
Very good.
Good night. Let me just validate and make sure